Turbine Fiscal Metering Tutorial. Metering System Design, Design Logic, Availability, Rangeability. Functional Design Basis. A fiscal metering system is not just a set of instruments, it is an engineered verification regime bound to custody, transfer, contractual compliance, and regulatory validation. At its core, turbine fiscal metering is designed to monitor liquid hydrocarbon flows with rigorous traceability and uncertainty bounds. The system is divided into two subsystems: I, the field-mounted skid with sampling and proving equipment, and T, the control and calculation infrastructure located in the CCR, LCR, or local room. This structure ensures operational transparency, enabling cross-verification of quantity, mass, volume, and quality, density, temperature, water cut, prior to final delivery. The entire measurement philosophy must be vetted early by authorities to ensure fast-track acceptance and error-free custody transfer. Availability as a measurement principle. Availability in turbine fiscal metering does not merely mean uptime. It defines the system's ability to continue valid measurements in degraded states. The architecture demands redundancy not only in components but also in power supply, instrumentation, and computation logic. Pressure and temperature transmitters, the highest range turbine meter, and the entire data acquisition logic must be fail-safe. Backup microcomputers and non-resettable mechanical counters ensure that a single electronic failure does not compromise data integrity. Redundancy allows uninterrupted operation during maintenance, calibration, or unexpected faults, essential for facilities where flow interruptions equate to contractual penalties or safety risks. Rangeability for flow dynamics. Rangeability isn't a metric, it's a design limiter and enabler. The system's maximum measurable capacity is derived from all operational meter runs at full scale, excluding standby or proving loops. The lower bound is governed by the smallest meter's precision, uncertainty at 2 sys. System rangeability is a critical parameter specified in the project requisition and is directly linked to metering uncertainty and fiscal compliance. The inclusion of multiple parallel streams, e.g., 3 times 50% or 2 times 100%, not only supports turndown flexibility, but also satisfies minimum rangeability requirements without sacrificing resolution or control performance. Validation and calibration discipline. Validation is not an episodic event, but a defined life cycle routine. All components, turbine meters, transmitters, densitometers, must be traceable to national standards, with calibrations performed at intervals based on drift analysis. Only components whose calibration exceeds maximum permissible error limits are adjusted. This maintains system continuity and audit trail clarity. The validation footprint of a meter includes not only calibration factors, but full metrology and geometry checks. Every calibration certificate must disclose systematic error trends, range-specific deviations, and measurement uncertainty to allow precise system-wide uncertainty reconciliation. Smart manual and alarm framework. Each fiscal metering station must maintain a station manual that transcends basic O&M guidance. It includes calibration logic, accuracy validation, alarm response triggers, and statistical control limits. These include the control limit, CL, a trigger for adjustment, and the significance limit, SL, a flag for long-term trend analysis. The manual defines when and how interventions are justified, how deviations are communicated to stakeholders, and how thresholds aggregate over a yearly average flow rate. This approach shifts operations from reactive correction to preemptive optimization. Inlet header and sampling logic. The inlet header forms the pre-measurement boundary and is embedded with critical instruments, pressure and temperature transmitters, gauges, and optional sampling lines. These are designed to be upstream of the metering and proving loops unless specified otherwise. The system must allow for safe, representative fluid sampling, particularly for density checks and custody quality analysis. The integrity of the inlet header instrumentation is pivotal in early anomaly detection and plays a direct role in flow control algorithms. Metering run architecture. Each parallel metering run is a fully self-contained measurement line, equipped with strainer, DP-monitored, flow straighteners, dual pickup turbine meters, pressure and temperature instrumentation, flow control valves, and leak check diverter valves. The dual pickup configuration allows for pulse verification integrity, a mandatory requirement under fiscal regimes. Metering runs are also equipped with thermal relief and isolation features, ensuring the system remains secure during shutdowns or proving transitions. By isolating metering lines, proving accuracy and redundancy are inherently supported. Meter prover integration. The proving system, bidirectional or compact, must comply with API MPMS Chapter 4 and be space optimized for offshore installations if applicable. The system includes dual redundant detectors, precision pulse counters, and interfaces for proving sequence automation. The prover must ensure 10,000 pulses per calibration run and a detector resolution matching this precision. Integration with the microcomputer architecture allows automated validation sequences with fail-safe abort logic for out-of-limit deviations. Sphere velocity, impact attenuation, and detector redundancy ensure repeatability without measurement bias or mechanical fatigue. Conclusion. The Turbine Fiscal Metering System is a precision-engineered infrastructure, not merely instrumentation, designed to meet the dual mandates of regulatory compliance and operational fidelity. Each subsystem, from metering runs to data logic, is calibrated not just for function but for defensibility under scrutiny. Through modular redundancy, rigorous validation, and digitally secured computation, these systems ensure that every unit of hydrocarbon measured is traceable, defensible, and contractually admissible. Validation framework and turbine fiscal metering, ensuring long-term measurement integrity. Structured validation as a lifecycle protocol. Validation in turbine fiscal metering is a deliberate engineered process, not a periodic correction effort. It defines how system accuracy is sustained over time. Manufacturers are required to submit comprehensive procedures that include calibration strategies, validation sequences, and decision-making logic for when and how adjustments should occur. These procedures must be transparent, auditable, and compliant with custody transfer regulations. Importantly, no adjustments to any component are permitted unless its calibration error exceeds predefined limits. This strict policy avoids unnecessary interference and preserves traceable calibration records. Traceability to national standards. All calibration procedures and equipment must be traceable to national or internationally accredited metrology standards. This traceability ensures legal defensibility, harmonizes practices across sites, and provides the necessary audit trail for regulators and contractual parties. Validation without traceability undermines the system's credibility and will not meet fiscal metering obligations. Calibration equipment and tolerance hierarchy. Calibration tools, when part of the supplied system, must carry valid certificates from national laboratories or accredited agencies. The equipment must have a measurement uncertainty no greater than 1/3 of the instruments being tested. For example, if a pressure transmitter has an allowed uncertainty of 0.3%, the calibrator must demonstrate no more than 0.1% uncertainty. These certificates must disclose systematic errors, the calibrated range, and the expanded uncertainty with 95% confidence, 2-SING coverage. This forms the benchmark for instrument acceptance and recalibration scheduling. Establishing calibration intervals. The initial calibration intervals for each instrument type must be defined in the tender and based on empirical drift behavior. Intervals must reflect both the inherent stability of the device and operational stressors. Over time, data trends will determine whether intervals can be extended or must be tightened. The system must therefore support adaptive calibration cycles informed by historical accuracy performance. Calibration records and audit storage. Every calibration, adjustment, or change to measurement parameters must be documented and stored securely for the duration required by law or agreement. These records must be easily retrievable and structured to support external audits. Parameters such as calibration factors, drift data, instrument replacement, and deviation trends must be included in a centralized database accessible to approved parties. This reinforces system accountability and enables forensic analysis in the event of discrepancies. Each turbine meter must undergo initial calibration against a recognized standard meter. The result is a performance footprint that includes calibration factors and full geometry verification. This initial fingerprint acts as the reference for future proving and diagnostics. Any future deviation from this footprint must be investigated, documented, and approved before system recommissioning. The fingerprint protects the meter's identity and confirms whether shifts in measurement are due to aging, fouling, or mechanical degradation. Uncertainty compliance and system integrity. Turbine meters and all secondary instrumentation must meet the overall metering system's uncertainty specification. Components cannot compensate for each other. Errors must not cancel out. A transmitter reading low cannot be accepted simply because a turbine meter reads high. Each component must independently comply with its maximum permissible error. The system must be free from compensatory errors to retain certification. Comprehensive uncertainty analysis. The manufacturer is responsible for submitting a full uncertainty analysis, quantifying the contribution of each metering component. This analysis must include statistical treatment, coverage factor 2 Siemens, sensitivity coefficients, environmental effects, and linearity deviations. The result must show that cumulative uncertainty lies within contractual thresholds. Without this analysis, system approval for fiscal use is incomplete. Station manual as a diagnostic backbone. A dedicated station manual must be developed, detailing operation, calibration, validation, maintenance, and documentation procedures for every primary and secondary measurement device. This manual must cover signal transmission checks, statistical diagnostics, drift response thresholds, and alignment with fiscal audit requirements. It must be precise enough to allow repeatable actions and flexible enough to accommodate future instrument upgrades or regulatory changes. Control limits, significance limits, and response logic. Intervention rules must be encoded in the manual using two parameters. Control limit, CL, a deviation threshold that justifies a one-time adjustment of an instrument. Significance limit, SL, a deviation trend that, if consistently exceeded in the same direction, mandates adjustment even if CL is not breached. Each instrument must have CL and SL values defined, documented, and reviewed periodically. A comprehensive escalation procedure must be defined for when these limits are exceeded, triggering revalidation, recalibration, and notification to stakeholders and regulatory bodies. Defining system-wide deviation boundaries. In addition to per-instrument thresholds, the entire measurement system must have a maximum allowable deviation defined for averaged yearly flow rates. This overall limit ensures that minor instrument drifts do not aggregate into unacceptable fiscal errors. Should system deviation exceed these bounds, corrective action, including recalibration of individual components and reassessment of uncertainty models, must be taken. Intervention policy and stakeholder notification. Measurement deviation beyond agreed thresholds triggers not only technical response, but also communication duties. All stakeholders, including commercial parties and authorities, must be notified through predefined channels. The policy must define who is responsible for evaluating, documenting, and reporting such events and what format the communication must follow. This guarantees transparency, contract adherence, and legal defensibility. Inlet header configuration and instrumentation design. Measurement boundary and system initiation. The inlet header defines the upstream measurement boundary and establishes the metering system's baseline conditions. It is not merely a flow entry point. It is the convergence zone for pressure, temperature, and sample stream instrumentation that anchors the metering logic. The accuracy and reliability of these measurements have a direct influence on calculated mass, density corrections, sampling quality, and ultimately custody transfer validity. Instrumentation for primary parameter acquisition. The inlet header must be equipped with a calibrated pressure transmitter and analog pressure gauge, each providing redundant verification of line pressure. Temperature measurements require both a transmitter with a thermowell and a mechanical temperature indicator, each installed in separate thermowells for cross-checking and diagnostic transparency. The physical separation of thermowells ensures independent sensing and prevents common mode failure. Sample stream extraction and analyzer integration. A dedicated sampling line must be included to serve analyzer systems, such as online densitometers, water cut analyzers, or composite samplers. The extraction point is typically located upstream of the meter runs and prover loop to reflect the fluid condition prior to any metering bias or mechanical interaction. If required by the process or installation constraints, the sampling point may alternatively be located downstream, provided it remains representative and justified in the sampling protocol. designed for flow continuity and signal integrity. The inlet header must be designed to ensure steady, non-pulsating flow to downstream components. It must prevent phase separation, entrained gas, or localized pressure drops that could affect sensor performance or sampling reliability. All instrumentation signals must be routed through shielded earthed cabling to the microcomputer system, preserving signal fidelity for computation and logging. Pressure and temperature sensor configuration. The pressure transmitter must offer digital signal output with analog redundancy 4 to 20 milliamps and support local diagnostics for drift, calibration status, and zero check functionality. The temperature transmitter must use a PT100 RTD element interrogated via a 4-wire circuit to minimize error due to lead resistance and to enable precision readings across narrow thermal spans. Process isolation and safety provisions. Each instrument must be isolatable via block valves with vent and drain ports to allow safe maintenance without depressurizing the entire header. These valves must be installed in compliance with piping class specifications and allow zero leakage isolation. For systems handling volatile or hazardous fluids, thermal relief valves and hazardous drains must be included to protect against trapped pressure or accidental overtemperature conditions. Foundation for custody measurement chain. Because inlet header conditions are the baseline for all subsequent volumetric and mass flow calculations, errors or inconsistencies at this point can propagate through the entire measurement chain. The inlet header is therefore engineered as a high-integrity control point, equipped, verified, and installed to eliminate ambiguity and to satisfy both engineering and regulatory standards. Metering run architecture and functional integrity, parallel run configuration for redundancy and turndown. Each metering run operates as a self-contained measurement line engineered for accuracy, redundancy, and maintainability. Runs are arranged in parallel to handle a wide turndown range and to ensure uninterrupted operation during proving, maintenance, or fault isolation. Design typically follows 2 times 100% or 3 times 50% configurations to provide both capacity and failover flexibility, while minimizing rangeability degradation during partial load scenarios. Component layout for precision and flow conditioning. Each run is fitted with an inlet valve, allowing isolation without system shutdown. Downstream, a stainless steel strainer with differential pressure monitoring protects the turbine meter from debris and fouling, preserving rotor performance and preventing damage. The strainer must be installed with sufficient access for basket removal and cleaning. Flow straighteners, compliant with ISO 2715, are positioned upstream of the turbine meter to remove swirl and profile distortion. This ensures that the velocity profile remains within design limits and that the meter receives a stable, symmetrical flow across its rotor blades. Minimum straight lengths of 10D upstream and 5D downstream must be maintained, where D is the pipe's internal diameter. Turbine meter assembly and signal redundancy. Each turbine meter is equipped with dual magnetic pickups and preamplifiers to enable pulse verification, fault detection, and redundancy. The design must support real-time pulse comparison for integrity checks and allow pickup replacement without meter removal. This supports SIL-level voting logic and ensures signal continuity during diagnostics or field servicing. Instrumentation for process compensation. Each metering run includes a pressure transmitter and pressure gauge to measure local line pressure, along with a temperature transmitter and temperature indicator housed in independent thermowells. These values are used by the microcomputer to compensate for temperature and pressure effects on fluid density, enabling accurate mass and corrected volume computations. Flow control and isolation mechanisms. A pneumatically actuated flow control valve regulates throughput during proving and stabilizes flow during transitions. Side-mounted declutchable hand wheels are required for manual override. Placement downstream of the turbine meter is preferred to minimize hydraulic disturbances upstream. The run terminates with dual outlet valves, one for mainline flow, one for prover diversion, both fitted with leak check provisions to ensure seal integrity prior to proving. These valves must also include position feedback and seal failure alarms. Safety and thermal protection. Each metering run must be equipped with thermal relief valves to protect against pressure buildup from trapped liquid exposed to temperature rise. These valves discharge to a hazardous drain or flare system in compliance with site safety requirements. Meter prover integration and calibration assurance. Prover type selection and compliance. The meter prover is a critical calibration component that ensures the metering system's traceability and legal acceptance. Unidirectional or bidirectional mechanical displacement provers are standard, as defined in API MPMS Chapter 4. For offshore or space-constrained facilities, compact provers may be used if approved by both fiscal authorities and the project principal. Regardless of type, the prover must be integrated downstream of the metering runs and be representative of the same process conditions as the meters it calibrates. Pulse resolution and volume certainty. The prover must be capable of generating a minimum of 10,000 meter pulses per calibration run to ensure statistical confidence. The sphere travel length, or effective calibration volume, must be at least 10,000 times the detector's repeatability. This ensures that each K-factor calculation is derived from sufficient pulse density and detector resolution, eliminating quantization error or switching lag effects. Sphere velocity must not exceed 3 meters per second to maintain stable flow and avoid mechanical wear or hydraulic shock. Detector redundancy and fault isolation. Each end of the prover must have 2 independent detector switches. This dual detection architecture prevents functional loss in the event of a switch failure and supports fault-tolerant proving sequences. Detector heads must protrude into the bore to guarantee actuation across all flow rates. Weatherproofing and corrosion resistance are mandatory for long-term outdoor deployment. 4-way valve and diverter logic. For bidirectional provers, a 4-way flow diverter valve must meet API Chapter 4 specifications and be integrated into the prover automation sequence. The valve must operate without introducing shock, dead zones, or hydraulic discontinuities. Its actuation must be monitored and seal integrity verified during each proving cycle to ensure no bypass leakage. If valve performance is compromised, the proving sequence must be aborted and flagged for operator intervention. Internal coating and integrity assurance. The internal surface of the prover must have a uniform bore with a non-porous, chemically resistant coating. The coating must resist explosive decompression and retain integrity across the full design temperature and pressure range. All surface preparation, application, and repair procedures must be documented and approved. The coating ensures that sphere travel is consistent and not affected by friction variations or degradation over time. Sphere guidance and wear prevention. Guide bars or tees must be designed to center the sphere reliably without inducing damage, deflection, or deformation. These mechanical elements must be optimized to maintain contact without abrasion and to prevent misalignment during high-flow proving runs. Their geometry must be compatible with the prover's bore and sphere design to avoid false detector actuation or wear-induced errors. Calibration interface for master verification. Prover piping must include standardized connections for recalibration against a portable master prover or traceable reference meter. These provisions support periodic verification campaigns and regulatory audits, ensuring long-term credibility of the prover volume and derived meter factors. Calibration procedures must be documented and align with national standards.